Hello students, good morning. So today we will continue with our discussion on magnetic field in magnetic media. Okay, different media. We discussed the different type of magnetic material, paramagnetic material, then diamagnetic material. Then we use the concept of magnetic susceptibility, how susceptibility can be expressed in terms of magnetization and magnetizing field H. Okay, chi is equal to H by M. So this way, chi is equal to M by H. So this way we created many relations in the previous module. Here we will see uh, what is called a non-linear magnetic medium. What is meant by non-linear magnetic medium? Okay, and how that is connected with the ferromagnetism. How that is connected with the ferromagnetism. And we have seen previous class, magnetization is proportional to magnetizing field. And you can make it a relation form. Magnetization M is equal to chi M into H. But chi M is called magnetic susceptibility. So we can say that here there is a linear relation between M and H. M is proportional to H. Or in other words, if you draw a graph between H and M, you will get a straight line. You will get a straight line. Understand? So any material that satisfies such a linear relationship is called a linear magnetic medium. In a linear magnetic media, magnetization M will be directly proportional to H. Or you can write M is equal to chi M in H. But there are certain media where this is not valid. This is not valid means M is not proportional to, directly proportional. In other words, M can have any non-linear proportionality. That means when you draw graph between H and M, you may get a curve which may not be a straight line. You may get a curve which may not be a straight line. Then we call it is a non-linear magnetic material. And moreover, where without an H there can be M. That means without applying a magnetic field there can be magnetization in such material. That means they have inherent magnetic property. So such materials are called non-linear magnetic material. So in non-linear magnetic material, M need not be directly proportional. Instead, can have a quadratic or cubic relation. Quadratic means that it may not be a straight line, it may be a curved. Okay, understand? So like that. So all ferromagnetic materials are examples for non-linear magnetic material. Ferromagnetic material, you know, examples are shown here: iron, steel, nickel, cobalt, gadolinium, and the other one is dysprosium. These are all elements in the periodic table of very large number of applications. Okay, iron and nickel, you know very well. Cobalt also, you know. Gadolinium, you may not be so familiar, but it is used in high-end research applications in cryogenic technology. And another one is a dysprosium that is used for making medicines for injecting into human body. Okay, whenever you do some scanning, okay, MRI scanning, you get medicines made of dysprosium. Dysprosium is denoted with the letter D1. So these are all ferromagnetic materials. Okay, and they do not require an external magnet field to sustain their acquired magnetization. That means once they are magnetized, even if you withdraw the applied field, there will be magnetic field, there will be magnetization inside the material. Whereas paramagnetic or diamagnetic material, The moment you withdraw the applied magnetic field, it will lost all the magnetic property. But ferromagnetic or non-linear magnetic field don't lost their inherent or gained or acquired magnetic field or magnetization. That is an important difference. For example, here we can see, here we try to elaborate the non-linearity problem. In a non-linear material, if you increase the H applied magnetic field, M will increase, of course, but M is not linearly increasing. If the increase is linear, you should get a straight line like this. You should get a straight line like this. But instead of that, here the relation is non-linear, so a curve is obtained. A curve. It is not a straight line. Okay. So the rest of the graph we will explain very shortly what is meant by all the other rest of the curves. So that is the meaning of non-linearity. In simple terms, you can understand what is non-linear. The relation between M and H is not a straight line. That is the meaning of non-linearity. And examples we quoted ferromagnetic materials are all non-linear magnetic materials. Okay. So in a linear medium, alignment of atomic dipoles are maintained by a externally applied magnetic field. For maintaining magnetic dipoles in a particular direction, you have to constantly apply a field. Understand? Without field, you cannot maintain magnetic dipole alignment. But in a ferromagnetic material, without external magnetic field, also magnetization can be sustained. No external magnetic field is required to sustain the acquired magnetization. Understand? So once acquired, even if you withdraw the applied field, you can maintain a magnetization. And moreover, similar to paramagnetism in ferromagnetic materials, this property is associated with the magnetic dipole moment of the unpaired electrons. Okay, unpaired electrons, what happens? They have spinning property. They spin. Every spinning electron is a micromagnet. So, with respect to the applied field, they can be put rigidly in a particular direction. So, they remain there. Understand? That is similar to paramagnetic. But still, there are certain differences at the atomic and crystal level orientation. In paramagnetism, once applied field is withdrawn, immediately all the micromagnets go in random fashion. But in ferromagnetic material, the moment you withdraw the applied field, all micromagnets are not getting into random motion. Okay, they are not getting in. They are still aligned in certain particular fashion. There is a residual magnetic property. Okay, that's called a residual magnetism. Residual means something remained back after the application of the applied, the withdrawal of the applied. So that is that. And again, it is a very strong interaction between the neighboring dipoles in a ferromagnet that makes it different from a paramagnet, where dipole-dipole interactions are not strong. This is one of the major differences. Dipole-dipole interaction is very strong in ferromagnetic materials. That is why we are readily getting aligned in a particular fashion. They are strong. Okay, this dipole-dipole interaction cannot be explained using classical theory. We need quantum mechanical theory to explain this principle, this phenomenon. In fact, okay, so we say that in ferromagnet, each dipole likes to point in the same direction as its neighbors. Okay, just they are looking at the neighbors. Whatever they do, they are imitating it. Okay, just like the students in an assembly, when the leader says that assembly attention, all the students come in a straight, upright fashion. Same way here also, the moment you apply the field, all the micromagnets likes to be in a particular orientation. And even microscopically, this alignment can be observed. Okay, many scientists have observed this alignment using different instruments, and one can see that or how the magnetic dipoles are aligning in a particular fashion if you use certain microscopic instruments. Okay, And why this is possible in ferromagnetic material? That is because if you look into the magnetic material crystal wise, the entire bulk of a crystal is divided into small domains. Okay, just like a dry paddy field, if you go in a summer season, you can see cracks, random cracks, how they are random cracks in paddy field. Same way here also they are randomly divided. The entire bulk, suppose the is a say cobalt crystal. If you microscopically observe the cobalt crystal, you can see that the entire crystal is divided into number of domains. These are in fact three-dimensional domains. You can see such patches, random patches. And within each domain, the micromagnets are aligned in specific directions. In each domain, they are aligned in specific directions. So keep in mind that if you have not applied any field, they are aligned in certain random directions. Even though random, still in a particular domain, all the micromagnets are aligned in the same direction. But in the neighboring domain, they will be aligned in some other direction. So the moment you apply a field, what happens? All the alignments within every domain, the alignment comes to a particular certain direction, certain fixed direction. Before the field, you see the domains are randomly aligned. After the field, all the domains are in the same direction. This is a wonderful property of ferromagnetic materials. Okay, so we say that the dipole alignment occurs in small patches. That patches are called domains. Actually, they are not two-dimensional patches. They are in fact three-dimensional patches. Okay, and each domain contains billions of dipoles, all lined up in certain specific directions. Okay, even though symbolically we showed with three lines, don't confuse that. There may be billions of micromagnets in each domain. Okay, and in each domain they are aligned in specific directions, not in a common direction. And these are visible. Okay, many by certain techniques you can make it visible, and each magnetic domains are randomly aligned. And under an externally applied magnetic field, these domains can align in a particular direction so that the material acquire a net magnetic dipole moment in a given direction. The moment you apply a field, external field, we show with B0. So, and magnetic domains are separated by domain boundaries are also the, okay, these are the domain boundaries. From one domain to the next domain, suddenly the direction changes. Okay, the direction is gradually changing in fact. So still it's a physical fact. It's a domain boundary. Okay, these are all crystal property. A lot of things are that we studied in the crystal physics, and you will understand the reason behind it. Okay, this is a real photograph of a cobalt crystal, where you can it's a scanning electron microscope photograph. You can see the domain boundaries are clearly shown here. This is an exact actual picture. You can see the domain boundaries here. Okay, within any particular domain, magnetic spins are aligned in a particular direction. And we want to introduce a new term that is called a remnant magnetic moment. In ferromagnets, when the applied field is withdrawn, the induced magnetic moment is not completely lost. Okay, so it is known as remnant magnetic moment. Okay, so you apply a field, material will be magnetized, and then after you switch off the applied field, then there will be a magnetization left behind in the sample. That is called a remnant magnetic moment or remnant magnetization. Okay, the graph drawn between applied magnetic field and induced magnetic field or magnetic moment is called hysteresis curve. That is what we are going to study now. What is meant by hysteresis curve? You can apply a field that is denoted with H, and the resulting magnetization you can measure Okay, you can measure it. So you can draw a graph between H and M. Okay, you can apply a field, you can increase the H value, then M finally reaches a peak value. Thereafter you cannot increase M. So that is called a saturation magnetization. And once saturation reaches, you can reduce the applied H value. If you reduce, then you see M is not coming back to the same graph. Instead, M traces a different path. We call it BZ. Again, when H is 0, M is not 0. So this is called a remnant magnetization. Remnant magnetization. Even though the applied H is 0, but there is a non-zero M. This is what is called this value. Okay, AC is called a remnant magnetization. Again, if you reverse the H value, M will also get reversed. Okay, and finally at a point M becomes 0. You applied some field to nullify the magnetization. So this is called the coercivity. Coercivity. Again, if you increase the H value, M will increase in the opposite direction. Anyway, non-linearly, okay, curve is a non-linear curve, and again a saturation point is reached. Okay, so this is what is called a residual magnetization. Which one? This one. Okay, residual magnetization. We will discuss in detail now. Okay, let us discuss one by one. You can split up the graph into a number of segments. Okay, starting from 0 to A to B, then B to C, then C to D, then D to E, and then E to F, F, G, and G, D like that. Okay. So this curve is called hysteresis curve. What is the reason? The reason is that H and M are not same. There is a lagging between H and M. When H is maximum, M is not maximum. Similarly, when H is minimum, M is not minimum. When H is 0, M is not 0. So this lagging is referred by the word hysteresis. The actual literary meaning of hysteresis is lagging behind. So here it means there is a phase difference between H and M. When H is 0, M is not 0. When M is 0, H is not 0. So that phase difference is called referred by hysteresis. Now let us study the curve one by one, starting from A. Okay. Ferromagnetic material can be magnetized and demagnetized by applying suitable field. Okay. So in the figure you can see from A to B. Here at the point B, what happened? M is maximum, and beyond that, if you increase the applied field H, M is not going to increase and remain that value. That is called a saturation point, and M at that point the M value is called a saturation magnetization. Saturation magnetization. Okay, keep in mind what is magnetization. Magnetization, total magnetic moment per unit volume. Okay, you need to calculate the magnetic moment, divide it with the total volume of the specimen, you will get a magnetization. Okay, and again after that you can reverse the you can decrease the H value. You can decrease the H value. At B now, if H is reversed, by reversing the current, original path will not be reduced. Okay, or if you decrease the current, decrease the H value, it will not go to the A value. It will take another path. The path you can call BC. This is an experimental graph. Okay, BC. Now you can reverse the H value in the opposite direction. Even though H is 0, M is not 0 here at that point. This value M is called remnant magnetization, as we have already discussed. Okay, and when you reach D, at D M is 0, but H is not 0. H is opposite and has a definite value. Okay, that H value is called coercive magnetism. Okay, the magnetic field, applied field required to remove the entire magnetization. Coercivity is the magnitude of the magnetic field required to remove completely the magnetization. That is called coercivity. And at the point E, you can see the value from is maximum, and beyond that M remains invariant irrespective of the value of H. Invariant means M is not increasing after that, it is remaining there. Whatever be the H value, you can increase H, it doesn't make any effect on M. Then you can reduce the H, again bring to 0. When H is brought to 0, M is again not 0. M is a non-zero value. This is again a remnant magnetization or residual magnetization. Okay, and when H is further reversed and reduced, M decreases at the point F, which is as a remnant magnetization. That is what is shown. Okay, and beyond that, if H is increased, what happens at the point G? At the point G, M is 0, but H is a non-zero value. So this again is a coercive. Okay, this again is a coercive in the positive direction. And you see, the graph has not come back to the origin at the point A. It is now taking another path to the GB. Okay, you get a closed path. So it is not retracing. So it is not, you can say it is an irreversible process. So instead of that, you get a loop like this. A beautiful loop you are getting, having a certain symmetric shape. So we call this a hysteresis loop. Hysteresis loop. The reason for the word hysteresis I have already told you. Here there is always a phase lag between H and M. Okay, phase lag. When H is maximum, M is not maximum. Similarly, when M is maximum, H is not necessarily maximum. This lag is referred as the hysteresis. Okay, that's why the word hysteresis is coming. So we have a small assignment, a simple assignment. Prepare a brief report on ferromagnetic domains. Already I have given certain comments on domains, magnetic domains. Still, I would advise you to make some Google search or read some books and write a interesting, very attractive report on ferromagnetic domains. You can even include photographs or like that, but still make an attractive report on ferromagnetic domains. A very important research area also. But don't go for any research level publication. You will get a very interesting report in websites, many websites, and many books also. Try to make an A4-page report on ferromagnetic domains. You will enjoy it. Okay. So with this remarks, let us conclude today's session. Have a twice or thrice you watch the video and enjoy the topics. Thank you all of you. See you again.